So I want you to imagine something for a second. Try to picture strapping a multi-billion-dollar piece of incredibly delicate, highly sensitive equipment to what is fundamentally a massive and highly controlled chemical explosion.
Basically a bomb.
Right, exactly. And you are about to shoot this equipment straight up at thousands of miles an hour, punching right through the atmosphere to hurl it into an absolute vacuum.
It is terrifying when you really frame it like that.
It really is. And here's the truly scary part. Once it's up there, repairs are completely impossible. I mean, there's no roadside assistance in orbit. You just have to sit back, watch the telemetry stream across a monitor, and, well, hope that every single microscopic piece of that equipment functions perfectly on the very first try.
Yeah, it's a phenomenal engineering reality to wrap your head around, because aerospace engineering operates in an environment that is just entirely devoid of second chances.
Zero margin for error.
Zero. A single sheared bolt or, a micro fracture in a strut, that doesn't just mean a delay. It means a total catastrophic mission failure.
Which is exactly the core focus of our deep dive today. We are unpacking a really comprehensive industry overview on aerospace simulation and force measurement in space exploration.
It's fascinating stuff.
It is. And our mission today is to figure out exactly how engineers recreate the unforgiving, frankly lethal harshness of space right here on Earth, long before a rocket ever reaches the launch pad.
Right.
We're going to explore what is essentially the invisible nervous system that makes all of these simulations possible. Specifically, we're looking at the precision force sensors and the interface products that are doing the incredibly heavy lifting behind the scenes.
Because measuring those forces with absolute uncompromising precision, that is the only thing standing between a successful deployment and a multi-billion-dollar debris cloud.
Exactly. And even if you are never going to launch a rocket yourself, understanding how these engineers measure, anticipate, and prepare for completely unpredictable extreme environments, it really changes how you view reliability in everyday life.
Oh, absolutely.
Whether you're building out a complex software architecture, designing a physical product, or just stress testing your own business's supply chain, the methodology of preparing for the absolute worst is incredibly applicable.
Yeah, the principles translate everywhere.
Okay, let's unpack this. I want to look at the physical brutality of simply leaving the planet first, because we get so caught up in the romance of spacewalks and planetary rovers that we forget getting off the ground is, it's one of the most violent physical events a structure can endure.
Oh, without a doubt. The launch sequence subjects a vehicle to just a symphony of destruction.
A symphony of destruction, I like that.
It's true. You have these enormous, sustained structural loads generated by the engine thrust, which is pushing millions of pounds upward.
Right.
And then you have the violent aerodynamic forces as the nose cone punches through the increasingly thin atmosphere. And add to that the acoustic vibration.
Wait, acoustic? Like the sound?
Yeah, the sheer sound of the rockets is actually enough to tear metal apart if it isn't properly dampened. Plus wild temperature swings all happening at once.
I've always thought of it like, it's almost like trying to design a multi-billion-dollar suspension bridge, folding it up into a compact briefcase, shooting that briefcase out of a cannon, and then just expecting it to unfold and operate perfectly in a vacuum.
That captures the mechanical anxiety perfectly. And to ensure that, folding bridge survives the cannon blast, engineers subject every critical structural component to simulated launch and landing events in these massive testing chambers on Earth.
See, this is where I push back a little, or at least where I get confused.
Okay, go ahead.
Because I look at the massive supercomputers we have today, right? We can digitally simulate the collision of entire galaxies or map the human genome in hours. It feels almost, primitive that we still have to physically shake a piece of titanium on a test stand to see if it breaks.
I get that.
Why doesn't the math just work out of the box? Why do we still need physical load cells to validate something a computer can simulate in seconds?
What's fascinating here is that a computer model, no matter how sophisticated it is, relies on an assumption of perfection.
What do you mean by perfection?
Well, the software assumes the titanium alloy is perfectly uniform down to the molecular level. But the physical world is inherently messy. Real materials have microscopic grain variations.
Oh,
The
right.
manufacturing process introduces tiny thermal stress fractures. Or maybe a microscopic bubble of gas might have been trapped in the metal during casting.
things the computer literally couldn't know about.
Exactly. Finite element analysis on a computer cannot predict those unique microscopic flaws in a specific piece of metal.
So the computer provides the theory, but the metal provides the reality.
That is exactly it. Therefore, engineers use physical interface, low profile, and mini load cells to measure the actual violent forces acting on these components during a physical simulation.
And a load cell as well, for people who don't know, what is it exactly?
A load cell is essentially a block of highly engineered metal with an electrical circuit bonded to it, which is called a strain gauge. So when the massive hydraulic press of a test stand applies force to the rocket component, the load cell bends microscopically. And that bending stretches the strain gauge, which then changes its electrical resistance.
So it basically translates a physical bending force into a digital electrical signal that the computers can read.
Yes, they take that real-world electrical signal and compare it against the pristine computer model.
Got it.
If the physical load cell says a strut deformed by 2 millimeters under 100,000 pounds of thrust, and the computer predicted 0.5 millimeter, the math is wrong. You halt the launch, redesign the strut, and try again.
So you are fundamentally checking the supercomputer's homework using brute physical force.
You really are.
That's incredible. Okay, so let's follow the timeline here. The load cells have validated our math, the structural integrity holds, and the spacecraft successfully survives the cannon blast. We are in space.
We made it.
Now we introduce an entirely different, incredibly complex payload into the equation. A human being. We evolved for 1G. We didn't evolve to float in microgravity or to walk on the surface of the moon or Mars. So to keep astronauts alive and capable of actually working, we have to hack gravity here on Earth for their training.
And hacking gravity is a fascinating dynamic force measurement problem, because you cannot just suspend an astronaut in a giant swimming pool and call it a perfect simulation.
Right, because everyone thinks of those underwater training tanks.
They do, and they're useful, but particularly when preparing for lunar or Martian gravity, they fall short. Water provides drag and resistance that simply doesn't exist in the vacuum of space. And it certainly doesn't accurately replicate the feeling of weighing 1/6 of your normal body weight on the moon.
The source material actually dives deep into how this is solved mechanically. To simulate reduced gravity, facilities use an intricate web of support cables attached to the astronaut's harness.
Yes.
And to constantly offset the exact right amount of weight, they install an Interface 1100 ultra-precision universal low-profile load cell directly in line with those support cables.
And this is where the engineering becomes beautifully dynamic, because it cannot just be a static counterweight pulling up.
Right, because they're moving around.
Exactly. The astronaut is actively moving, jumping, kneeling, twisting to grab a tool. If the cable pulls up with a constant force, the moment the astronaut pushes off the ground, they would just fly upward uncontrollably.
So the system has to think.
It does.
The source notes the load cell is paired with an Interface 9870 high-speed, high-performance indicator. So if the load cell is like the nerve ending feeling the tension, this indicator acts like the brain.
That's a great analogy.
It is continuously measuring the applied force from the astronaut's erratic movements, crunching that data, and dynamically commanding the winch to adjust the upward pull in milliseconds.
Which means the astronaut experiences a seamless illusion. No matter how violently they move, the system adjusts the tension so rapidly that they genuinely feel like they're walking under the gravitational pull of another planet.
Here's where it gets really interesting to me. I am picturing this as a highly intelligent, invisible bungee cord. The astronaut is basically a high-tech marionette, but the strings are constantly calculating the physics of a different planet in real time.
Yes, and the precision required for that illusion becomes even more critical when training for extravehicular activities or spacewalks. Operating outside the protective shell of the spacecraft introduces a zero-margin environment.
Just stepping right into the void.
Exactly.
The source highlights that for spacewalk simulations, engineers use the Interface WSSB welded stainless steel S-beam load cell. It's essentially a steel block, shaped like an S that is incredibly sensitive to being pulled apart.
Right.
They use it to monitor the cable tension, and then they feed that data through a DMA2 DN-rail signal conditioner. Now, I assume a signal conditioner is basically a translator.
That is a great way to put it. The S-beam load cell is registering microscopic changes in tension, which create tiny, very fragile electrical signal. Now, a testing facility is full of heavy machinery, massive motors, and tons of electromagnetic interference. The signal conditioner takes that tiny, whispered signal from the sensor, cleans out all the static and noise, and amplifies it so the control computers receive a crystal clear data stream of exactly how much force is being applied.
Okay, I understand the mechanics of it, but I find myself wondering about the stakes here.
Yeah.
Let's say the gravity simulation is off by, 2 or 3%. It's a tiny fraction. Why go to the immense trouble of installing these hypersensitive S-beam load cells and signal conditioners just to shave off a tiny percentage of error in a training simulation? Does it really matter?
It absolutely matters, and the stakes are purely rooted in human muscle memory.
Muscle memory.
Yeah. Think about it. When an astronaut is suspended outside the International Space Station, their brain is managing a terrifying amount of sensory input. They rely heavily on the automatic muscle memory they built during hundreds of hours of simulation on Earth.
That makes sense.
So, if an astronaut trains to turn a critical locking lever in a simulation that has 3% too much resistance, their muscles learn to apply 50 pounds of force.
Right. And then they get into actual space.
And they apply that exact same 50 pounds of force because their muscles were trained to do so. But in the true vacuum, without that artificial resistance, 50 pounds of force might snap the lever clean off.
Oh, wow.
Or, conversely, they might apply too little force and fail to properly secure a tether that keeps them from drifting away. The force profile in the simulation must be mathematically identical to reality. If it isn't, the training is actively endangering the mission.
They are literally trusting their lives to the calibration of that S-beam load cell.
They are.
It is teaching their muscles the physics of a completely different reality. But, as capable as human astronauts are becoming with all this training, they are still basically fragile bags of water that require constant life support, radiation shielding, food.
We are very high maintenance.
We really are. And that biological fragility is driving the biggest shift in orbital mechanics today, which is handing the most dangerous work over to robotic systems.
The transition to autonomous robotic systems is the next major leap. We are looking at a future where robotic arms repair active satellites, assemble modular spacecraft in orbit, and conduct deep space maintenance.
Now, I look at these incredibly complex 6-axis sensors mentioned in the research, and I initially wondered if we are over-engineering this.
Really? How so?
Well, a human just uses their hand to push a door open or pull a lever, right? A robot is basically just pushing and pulling. Why does a robotic arm need an intricate, multi-directional sensor system just to turn a wrench?
This raises an important question about the physics of space. Consider the physics of turning a wrench in a zero-gravity vacuum.
Okay.
When you stand on Earth and turn a wrench, gravity anchors your feet to the floor, providing a counterforce. In space, if a robotic arm reaches out and turns a wrench on a satellite, there is no gravity to anchor the robot.
Oh, of course. For every action, there's an equal and opposite reaction.
Yeah.
If the robot twists the wrench clockwise, the torque will just spin the robot itself counterclockwise if it isn't compensating.
Exactly. The physics of rotational force, or torque, changes everything. The forces are not just linear pushing and pulling. A robotic joint operates in 3 dimensions. And the engineers use Interface's 680F series 6-axis Diina and flange type load cells for this exact reason.
Those 6 axes being the 3 directional forces, so up, down, left, right, forward, backward,
Yeah.
and the 3 rotational forces around them, pitch, yaw, and roll.
No, you got it. The 680F sensor measures the force and torque across all 6 of those axes simultaneously.
That's a lot of data.
It is. Imagine a robotic arm reaching out to dock with a satellite that is slowly tumbling. The moment the robotic hand makes contact, it is hit with a chaotic combination of forces. The satellite is pushing against the hand, but its rotation is also trying to violently twist the hand off its hinges.
And the robot has no skin. It has no nervous system to feel that twisting sensation. It only knows what the data tells it.
Right. So they run the data from that 6-axis sensor through a BX8 HD44 BlueDayQ series data acquisition system.
A data acquisition system.
Yes. This system is capable of capturing, graphing, and analyzing all of those complex forces in real time. It tells the robotic arm exactly how to adjust its grip and compensate for the torque.
So without that, it would just break things.
Pretty much. Without that multi-axis data stream, the robot would likely push with the correct amount of forward strength, but completely fail to counter the rotational twist, instantly snapping a delicate solar panel or an antenna.
It needs to feel the push, the pull, and the twist all at the exact same millisecond, basically replicating the intuitive feedback of a human wrist.
Precisely.
And this requirement for incredibly rich, complex force data, it isn't just for orbital mechanics, it applies to how we interact with alien surfaces too. Planetary rovers don't get the luxury of freshly paved roads. They are dropped into completely unpredictable terrain.
Oh, yeah. Navigating loose Martian regolith or jagged lunar rocks introduces profound mechanical stress. A rover getting its wheels permanently buried in soft sand is a multi-billion-dollar tragedy.
Because nobody is dispatching a tow truck to the Jezero crater.
Definitely not.
The source outlines a fascinating method for preventing this. Engineers build these massive test beds filled with simulated alien soil. But to get accurate data on how the wheels perform, they can't just measure the power the motor is putting out. They use an Interface T14 slip ring shaft-style rotary torque transducer, and they embed it directly inside the hub of the rover's wheel, right alongside the drive motor.
And placing the transducer directly inside the wheel is just a stroke of engineering brilliance.
Why is that?
Well, if you measure torque back at the main chassis, you lose fidelity because of the friction in the axles and the gears. By putting the sensor right at the point where the rubber, or in this case the woven metal mesh, meets the Martian dirt, you are measuring the absolute true torque being exerted against the ground.
I imagine a major headache here is the wiring. I mean, you have a wheel constantly spinning, grinding through abrasive sand, climbing over jagged rocks in a test chamber. You can't just run a bunch of delicate copper data cables off a spinning wheel. They would instantly tangle and snap.
Cables are the enemy of realistic mechanical testing. They restrict movement, they add unnatural weight, and they create major failure points.
Which brings in wireless telemetry. The source details how they pair the torque transducer inside the wheel with a WTS-AM1E wireless strain bridge transmitter module.
Exactly.
This tiny module broadcasts the real-time torque data to a WTS-BS handheld display.
So an engineer can literally stand next to the test chamber holding that display, watching a live graph of the wheel's torque as the rover struggles up a 30-degree incline of loose sand.
That's so cool.
They can instantly see if the wheel is gaining traction and moving forward, or if the torque is spiking wildly, which indicates the wheel is just spinning uselessly and digging a grave for the rover.
So they find the exact mechanical limits of the drivetrain here on Earth, so the autonomous driving software knows exactly when to back up and try a different route on Mars.
Yes.
Okay, so we have survived the launch, we have manipulated gravity for our astronauts, and we've given our robots and rovers the sensory input they need to survive. The final piece of the puzzle is shelter. Humans and machines need a place to live on these alien surfaces.
And constructing habitats on the Moon or Mars introduces a radically different structural engineering paradigm. We are completely moving away from the rigid heavy metal cans of the Apollo era.
Because the logistics of spaceflight demand it. The source highlights that future planetary habitats will be inflatable. They need to be incredibly lightweight and packed tightly to fit inside the payload steering of a rocket.
Right.
But once they are deployed on the surface, they inflate. And they are inflating in a near vacuum, which means the internal pressure required to keep humans alive is constantly trying to blow the habitat apart.
It's intense. You are basically inflating a highly pressurized balloon in an environment that offers zero atmospheric pushback.
Yeah.
The structural integrity of the fabric and the structural webbing that encases it is the only barrier preventing instantaneous explosive decompression.
And you can't simulate that by just pumping it full of air and stepping back to see if it pops.
No, the stakes are way too high.
So engineers use Interface LP stainless steel load pins, which are specialized force sensors shaped sort of like the steel pins used in heavy rigging. And they literally weave these load pins directly into the critical structural webbing of the inflatable habitats during the pressure testing on Earth.
Yes, and as they incrementally increase the pressure inside the habitat, those load pins are monitoring the astronomical tension pulling on the Kevlar-like webbing.
So what does this all mean? It's like they're giving a giant space-bound balloon its own biological nervous system.
That's a perfect way to describe it.
By weaving the sensors into the actual fabric of the structure, the habitat can effectively communicate its pain. It can transmit data showing exactly which seam is taking too much stress long before the fabric actually tears.
And real-time, embedded feedback is the only way to validate a flexible, non-rigid structure like that. If we connect this to the bigger picture, a massive trend making all of this possible is the miniaturization of these sensors.
Because aerospace environments have unforgiving spatial limitations. Every single cubic inch of a spacecraft or habitat is accounted for.
Exactly. Interface's miniature load cells provide the accuracy of the massive test stand sensors we talked about during the launch phase, but they are shrunk down to fit into the tightest, most complex mechanisms of a satellite or, an inflatable wall.
Wow.
And when you combine that miniaturization with the wireless telemetry we discussed with the rover wheels, you fundamentally alter the landscape of aerospace engineering.
Because you remove the physical constraints of testing.
Yes. Engineers conceal a complex rotating mechanism inside a cryogenic vacuum chamber, freeze it to -200 degrees, and still receive a flawless stream of wireless data detailing every ounce of force inside that mechanism.
The simulation is finally allowed to perfectly mimic the reality of space, unhindered by the bulky cables and heavy instruments of the past.
It changes everything.
It really does.
Yeah.
When you pull back and look at the entire picture, the violent launch validations, the dynamic gravity illusions, the multi-axis robotic joints, the wireless rover wheels, and the pressurized inflatable habitats, it crystallizes the true nature of space exploration. It is an exercise in anticipating the unknown through obsessive measurement.
Absolutely. The philosophical grandeur of space exploration is entirely underpinned by the grueling, microscopic realities of the physical world.
Right?
Every major milestone in space begins with a highly accurate force measurement on the ground. The precision of the sensors dictating the simulation is really the foundation upon which the entire aerospace industry is built.
If the physical load cell doesn't validate the math, the rocket stays on the pad. The map is invisible, but the physical forces are absolute.
Which leaves us facing a rather profound engineering hurdle for the future.
What's that?
Well, we have spent this entire discussion exploring how the success of our planetary rovers, habitats, and robotic missions relies entirely on our ability to perfectly simulate and measure every conceivable physical force on Earth beforehand.
Right. If we can't simulate it accurately, we can't trust it to survive.
But as our ambitions push us further out, past Mars and into deep space, or into the subsurface oceans of moons like Europa, we are going to encounter environments with fluid dynamics, pressures, and gravitational anomalies that are entirely alien to our current physical models.
Wow.
We might not even possess the foundational knowledge of how to simulate those conditions yet.
How do you build a physical simulation for an environment you don't even fully understand?
That's the question. How does the science of precision force measurement adapt when we are tasked with building spacecraft for conditions we physically cannot recreate in a laboratory on Earth? That is the monumental challenge awaiting the next generation of aerospace engineers.
It brings us right back to the beginning, really. We are strapping our most delicate, brilliant achievements to a controlled explosion, hurling them into an absolute void, and trusting that the microscopic sensors that proved our math on Earth were right all along.
Because in the dark of deep space, the laws of physics are the only safety net you have.
Something to ponder the next time you look up at the night sky.